Hey everyone, welcome to this first lecture of Calculus 2. So this is going to be a full course on Calculus 2. So it'd be roughly equivalent to the same lecture material you would get if you were attending like a university and you were maybe a sophomore at a university and you were studying Calculus 2. So this is going to cover everything under the envelope of Calculus 2 and possibly a few additional items that are frequently left out of Calculus 2. So this course is going to be a natural add-on to the Calculus 1 course that I also have available. And so if you've taken that course, this should feel very natural, same notation, same everything, kind of very fluid. It's just the next chapter in the calculus story. So this first lecture is, in this first lecture, we're going to introduce the idea of an antiderivative and equivalently, and otherwise known as, an indefinite integral. And so that's where we'll start. And so let's call this section 1.1, Antiderivatives and Indefinite Integrals. Okay, so we'll talk through these ideas first. So this is the natural starting point for Calculus 2. Now, I guess just a little bit of metadata on this. So Calculus 1 starts out with the idea of basically limits. Okay, we start with limits in Calculus 1, and then we move from limits into derivatives and differentiation. Okay, and we spend, maybe a third of the time on limits, and then the rest of the time, the rest of the 2/3 of Calculus 1 on differentiation. So this is all like under the heading of Calculus 1. And now what we're going to do is we're going to move into integrals and integration. Right, so this is kind of like, you can think of it like this: if derivatives are multiplication, integrals are division, or maybe if this is addition, this is subtraction. They're two sides of the same coin. They've got a relationship to one another that is very tight. And so we'll spend most of Calculus 2 working on integration, integrals, understanding what they are, what are a lot of the applications of them, etc., etc. And then after that, we'll spend some time on infinite series, which we won't get into that right now, though. But Calculus 2 really picks up, usually, with this idea of integration. Usually whenever you start integration, that's usually where you start Calculus 2. And it's not because there's any natural reason that this has to be the case. It's just that in the normally a course has a certain length, and that length is enough to get you through right about here, right? And then this one we'll pick up afterwards. Now, in terms of, I thought at the time when I was an undergraduate taking Calculus 2 for the first time, I did think it was harder than Calculus 1. In fact, I thought Calculus 2 was harder than Calculus 3. And I think that's a broadly held sentiment. It is a challenging subject. Integration is somewhat more complex, in my opinion, than differentiation as an idea. And a lot of the applications of integration are more complex as well. And also, calculating integrals is it can be much more challenging than differentiation. We'll see to all of that. You'll note all of these things as we're going through it. But on the other hand, so yes, Calculus 2 is more complex, but I do think it is the line in the sand where mathematics, in my opinion, starts to really veer into the more advanced, more like extremely compelling areas. So it's also, while it is more challenging, it is also well, you can definitely say, hey, I'm doing kind of the big boy stuff now. Like this Calculus 2 is very much the big boy stuff. So anyway, so let's go ahead and get started. That's just a little bit of background. It's not much, but let's go ahead and get started. Now, our first definition here is the definition of an antiderivative. So if I asked you what's an antiderivative, you might be able to tell me roughly what this definition is. Very, very straightforward. A function f is an antiderivative of f. So the way I'll say this is a function big F is an antiderivative of little f, okay, on an interval I if, now here's the thing, f prime of big F prime of x is equal to little f of x. And then for all x on the I, for all x in the interval. Okay, right, so there's the idea. So basically, big F of x is an antiderivative of little f of x if, when you differentiate big F, you get little f. Okay, so it's an antiderivative if this relationship holds. And then of course technically it would be based on intervals and da 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 da. But this is the big idea right here, right? So if you've got two functions, one of which we call little f, the other one we call big F. If when you differentiate big F you get little f, then big F is an antiderivative of little f. Okay, let's see an example. All this little f, big F talk is probably causing people's eyes to go cross. So let's say big F of x is equal to x cubed. Okay, now this is an antiderivative, okay, of 3x squared. Okay, so big F of x equals x cubed is an antiderivative of, I should say, little f of x equals 3x squared. Okay, because f prime of, so big F prime of x, that's the derivative, that's d dx of x cubed, which is equal to, as we know, 3x squared, which is equal to little f of x. Okay, so x cubed is an antiderivative of 3x squared. Okay, so you can it's kind of obvious what's happening here, but it can also, some of the nomenclature and the terminology can be a little strange. But basically, look, if you have a function and you differentiate it and you get another function, then the function you started with is an antiderivative of the function you got after you did the differentiation. Okay. So it's important to note, it's important to note that when we say that f is an antiderivative, that's very intentional language. So when we say that f is an antiderivative of f, what we mean, right, we're being very intentional in our language. What we mean is that it is not the antiderivative of f. So when we say that big F is an antiderivative of little f, we mean that there are more than one antiderivatives of little f. Okay, right. So that language, f is an antiderivative of big F is an antiderivative of little f. Well, that there's an implication there that there are more than one antiderivative, and that is in fact the case. Okay, so in the example we just looked at, right? In the example we just looked at, we saw big F of x equals x cubed was an antiderivative of 3x squared. But here's another one. Okay, so another one would be, let's call this F1. Another one would be what? X cubed plus 5. How about that? Also an antiderivative of 2x squared, right? What happens when I differentiate this? F prime 2 of x is d dx of x cubed plus 5, which is 3x squared plus 0, which is 3x squared, which is f of x, right? So here's another one, right? Could we go on? Oh yeah, sure, we could go on. Here's another one. Big F of 3, maybe that's x cubed plus 100, right? And so on. So we could obviously keep going in this manner, right? But hopefully, if you just kind of look at these three, you might be able to see that, well, there's a little bit of a pattern here, right? So in general, there's an infinite number of antiderivatives for f of x. So in general, there are infinitely many antiderivatives of f of x equals 3x squared. Okay, they all have a form, and that form is this: f of x, big F of x equals x cubed plus something, some constant. Okay, so here we had no constant, the constant of 0, you could say. Here we have a constant of 5. Here we have a constant of 100. You could also have constants that are negative, like negative 3.62, right? But no, so all of those would fit the definition of antiderivative for 3x squared, because when you differentiate them, you get 3x squared. So there's an infinite number of functions that could be differentiated to produce 3x squared, but all of them have this form. Okay. All right. So this leads us to our first theorem of Calculus 2. Okay. So, theorem. If f, big F, is an antiderivative of little f on an interval I, we'll say, okay, then g is an antiderivative of f, little f, if and only if g is of the form g of x equals f of x plus c. Okay, so this is kind of what we just said, right? And I should say for all x on I, for all x in I, and where c is a constant. Okay, so this is just like the most general way to say what we just talked about, right? All of this business up here, all of this stuff, it's all this idea. This idea is just kind of capturing all of that in a general, very general statement. Okay, so basically, if f is an antiderivative, if big F is an antiderivative of little f, then g is also an antiderivative of little f if it has the form big G of x equals big F of x plus just some constant. Okay, And in fact, so this is an if and only if statement, right? So that means it goes both directions. So if this is true, the first part is true, then it implies this. And the reverse also. If g of x equals big F of x plus c, then g is an antiderivative of f. Okay, so this is the idea. Now let's go ahead and let's prove this theorem. Okay, let's prove this. Let's try to see that this is true. Let's try to like work through the logic of showing that this is in fact a true statement. So we'll start by assuming this piece, this second piece. So we'll assume that g of x is equal to f of x plus some constant. So it has the form of f of x plus some constant. Well, it's very straightforward in this direction, right? So we'll just differentiate g. So then g prime of x is equal to d dx of big F of x plus c, which we know is f prime of x, right? Differentiate that part. And then what's the derivative of a constant? Plus 0, right? And then we know that f is an antiderivative, so we know that the derivative of big F of x is equal to little f of x. Okay, so obviously we can see that g prime of x is equal to f of x, and so if g prime of x equals little f of x, then g is an antiderivative. Okay, so we're done in that direction. Okay, and that's just as easy as recognizing this, right? It's really just recognizing that f is an antiderivative, and therefore it equals little f of x, and c is a constant, and the derivative of a constant is always 0. So that direction is really easy. So you can kind of think of this as the reverse direction. Now, what about the other way? Yeah, the other way is a little trickier, but it isn't. It's nothing we can't handle. So in the next direction, let's assume that g of x is an antiderivative of f of x, little f of x, right? So g of x is an antiderivative of little f of x, and so it's important to remember what does that mean, right? So that means that g prime of x is equal to f of x. So when we differentiate g, we get little f, right? So that's by definition, right? That's what antiderivative means. Now, sometimes it's important to keep in mind what we're trying to show. So we wish to show, what do we wish to show? We wish to show that g of x is equal to big F of x plus c. It has this form. Okay, so that's what we wish to show. So let's this is where we're headed. Okay, so let's define a new function, h of x. H of x is going to be equal to g of x minus big F of x. Okay. Now, if h is not constant, okay, it is not constant on the interval of interest, right? And this is an assumption, so let's assume this. Okay, if h is not constant on I, then there must exist a and b in I. Okay, so some real number a and some real number b in I, and we'll just say a is less than b, such that h of a is not equal to h of b, right? So this is super basic. I know we're kind of being pedantic about this, but let's recap here. So define big H of x equal to g of x minus big F of x. Okay, now the assumption here is that, f of x is an antiderivative and g of x is as well, right? So we're defining this h to be the difference between the two. Okay, now if h is not constant, right? So what we would expect here that, so kind of stepping outside of the proof for a second, what we would expect is that if these are two different antiderivatives of little f, then they should be the same except for some constant. Right? So what we're assuming here is that h is not constant. It's not a constant. And what we're going to do here, kind of the setup here, is that we're going to derive a contradiction based on this assumption. So if we assume h is not a constant, then we're going to derive a contradiction. Okay, so we make that assumption. We assume that h is not a constant. And what that implies, right, the implication of that is that there's going to be some a and b such that h of a is different than h of b. Okay, if h was a constant, if h of x was a constant function, then we couldn't say this. But if h of x is not a constant function, then this must be true. Okay? All right. So now let's take a look at what happens. Okay? So I'll bring the information back from the previous page. So there exists a and b in the interval I, and we'll just say a is less than b. They're just not equal. It's the important part. Such that h of a is not equal to h of b. Okay, this is all just basic logic here, hopefully. So h is differentiable. Okay, right? Obviously, it's a difference of two differentiable functions. So it's differentiable. H is differentiable. Right? And so if h is differentiable, then the mean value theorem applies. Okay, so h is differentiable. So by the mean value theorem, there exists a c and the c is going to be somewhere in the interval AB. So there's going to exist some real number c such that the derivative of h at c is equal to h of b minus h of a over b minus a. Okay. This is just the mean value theorem, right? This is back from Calculus 1. I think there's a whole lecture video on just called the mean value theorem where we talk about this. Okay, and so I'm going to take for granted that you've seen that. So this is true, right? So we can evaluate the derivative at a certain value, and it's going to be equal to basically this ratio. Okay, and it's non-zero, right? It's non-zero. Why is it non-zero? Well, because h of b and h of a are different, right? Put that in here. Because h of b is not equal to h of a. That's why it's non-zero, okay? Okay. All right. So then by assumption, this is what we have, right? By assumption, we know that g prime of x is equal to f of x. And we assume that g is an antiderivative, so this is true. It's an antiderivative of little f. And obviously, we know that f prime of x is as well. Okay. So g prime of x is equal to f of x, which is equal to big F prime of x. Okay, now what does that imply? Well, if that's true, obviously these two are equal as well. Okay, and so we can say g prime of c is equal to f prime of c. Okay, and so what does that tell us? Well, that tells us that h prime of c equal to g prime of c, minus f prime of c, big F prime of c, is equal to 0. Right, they're equal, right? So h was defined, remember, as the difference of these two, right? So if h prime of c is equal to this and this, they're the same thing, they must be equal to 0. So that means h prime of c is equal to 0. Okay, so what happens then, right? What happens then, right? So if h prime of c is equal to 0, this is going to imply, just to be clear, h prime of c is equal to 0. That implies a contradiction. Okay, what does it contradict? Well, right here. Right, it contradicts that part of it. It also contradicts a couple statements back where we said that h was a non-constant. Okay, so this implies a contradiction. Therefore, I guess what we could do is we must conclude that h is a constant. Okay, so what does that mean? Well, that means that we defined it like this: h of x is equal to g of x minus f of x. It's the difference between the two antiderivatives, our two distinct antiderivatives. And so, well, that just implies that some constant is equal to the difference. And that implies, of course, that g of x is equal to, just a little bit of algebra here, f of x plus c. All right, and that's the outcome. That's what we wanted. And so what does this mean? Well, it means that any antiderivative is going to be of the form f of x, big F of x plus c. Right? So essentially what this means is that we can represent the entire family of antiderivatives of a function by just adding a constant term to a known antiderivative. So let me write that down. That's kind of the big idea of this first, one of the big ideas of this first section. So we can represent the entire family of antiderivatives of a function by adding a constant term to any known antiderivative of the function. Okay, right, so that's nice. Right, so even though there are infinitely many antiderivatives for a given function, there's one form. All right, those can all be reduced to a very particular form. Okay, so let's see. Let's do an example here. Okay, so knowing that d dx of x squared is equal to 2x gives us all of the allows us to immediately know all of the antiderivatives of f of x equals 2x. So knowing that d dx of x squared equals 2x, all the antiderivatives of f of x equals 2x can be represented by g of x equals x squared, right, plus some constant. That's what the last theorem showed us. They all have the same form, right? There's infinitely many of them, but the only thing that distinguishes them from one another is the addition of some constant. All right, so this constant has a name, and it's called the constant of integration. It's called the constant of integration. Okay. All right. So, so some terminology here. So you got the constant of integration. That's what, that's the plus c at the end of all of these antiderivatives. And another term to know would be, so the family of functions. Represented by, g of x, in this case, x squared plus c. This is called the general antiderivative of f. All right, so the whole class of functions is called the general antiderivative of f. Okay, and then another thing here, g of x, big G of x, equal x squared plus c is the general solution of the differential equation g prime of x equals 2x. Okay, so suddenly we were talking about differential equations. Well, we talk about them a little bit because they play in nicely as we start to define what we mean by an indefinite integral. So what do we mean by a differential equation here? Well, a differential equation in x and y, it's just an equation that involves x and y and also derivatives of y. So it's an equation that involves x and y, but also basically y prime. Okay, examples. What do I mean by this? Well, y prime equals 3x is an example of a differential equation. Another one would be y prime equals x squared plus 1, another differential equation. So these are differential equations. So when you get into, after calculus 2, there's many people take calculus 3 right away, but you can also, and I think it might be advisable to take a different course between those two to take differential equations. Usually it's a standalone course. And it's usually called ordinary differential equations. There's also partial differential equations, which are somewhat more complex. And people don't usually take those until much later. But ordinary differential equations explore equations like this and how to solve them. And we're not going to get deep into solving differential equations in this class. We will talk about it a little bit, but this is more like a matter of motivation. So, an example: find the general solution of the differential equation y prime equals 2. Okay. All right, so you've got a differential equation, y prime equals 2. So dy over dx equals 2. So what's the goal here? Well, to begin, we want to find, what we're doing is we're looking for a function whose derivative is 2. Find a function whose derivative is 2. Okay, so there's lots of examples, right? One example would be y equals 2x. Okay, that's one example. So then, obviously y equals 2x. If you differentiate, you get y prime equals 2, right? Okay, so that would be one solution. We want to find the general solution. So by the previous theorem, the general solution, right, is just a particular antiderivative plus a constant. Okay, so the general solution to this differential equation is y equals 2x plus a constant. Okay. All right. So when solving differential equations such as this one, but in general, when solving diff-EQs like dy dx equals f of x, it's usually convenient to write it like this. It is usually convenient to write dy equals f of x dx. Okay. It's usually a convenience when solving differential equations. So this would be like your y prime right here, right? So you got the y prime up here. So the dy dx would be like the y prime, but you can break that thing apart. It's usually convenient to leverage this notation. And so this operation of that, what we just performed, this operation of finding all solutions of this differential equation, this operation is frequently called antidifferentiation, but actually much more commonly this is what's called indefinite integration. Okay, so this operation is called indefinite integration. Okay, so this operation of identifying the general solution to a differential equation of this type is sometimes called antidifferentiation, but most of the time people will refer to this as indefinite integration. Okay, so we're getting somewhere now. Okay, and it's a little bit of a slog, kind of trying to set this up, but this is what we mean by indefinite integration. And so if we have dy equals f of x dx, right? A lot of times the notation, what people will think of here is you integrate both sides, and we'll get into this symbol in a second. And when you do this side here becomes just your y, and you have this. So this is the integration symbol. It's kind of like a big L, actually, and I believe the origins of this notation are Leibniz, and I believe it is an L, named after, or so named by Leibniz in honor of himself. So I believe this is Leibniz. Leibniz is the origin here. So, so this is the idea. So you have a differential equation, and starting with this differential equation, you can identify the general solution, the family of antiderivatives that are solutions to this differential equation, and that operation of doing that is called indefinite integration. Indefinite integration. Okay, and this is kind of the way you'd want to think about it. We'll get into something, we'll talk about this more in a moment, actually. But so you start with this differential equation, you integrate both sides, which is this operation of finding the antiderivatives, and that solution to the differential equation is then basically can be written in this form. So you've got y equals the integral of f of x dx. Okay, so let's talk about some basic integration rules. That's kind of where we're heading next. Okay, basic integration rules. Now, Integration and differentiation are going to be inverse. They have inverse natures. Okay, so the inverse nature of integration and differentiation can be verified as follows, right? So, right, it can be verified. So let's talk about that for a second. So recall, f is an antiderivative of f, of little f, if the big F prime of x equals little f of x. Okay, right. So if that's true, then here's what we have. So the integral of little f of x dx is equal to big F of x plus c. Right. So this is just the general form of the solution to dy equals f of x dx. So taking this piece here, okay, well, we know this, right? So we know that little f of x is equal to big F prime of x, right? So, right, that works, just substituting those two. Okay, and we know, of course, that this is true. This thing here is equal to this, right? And so, of course, this whole thing is just like so, right? And now look at what what have we shown here, right? So if we take the integral of a derivative, we get back the original function, right? So we've got the derivative of big F prime of x. When we integrate that, we get back to regular F prime of x. So this is one way to see this kind of the relationship between these two. Okay, I think a somewhat cleaner way to see it would be to kind of do it in a different way, to take the differentiation outside of the integration. So another way to look at it is the following. So if we start with ddx of the integral of little f of x dx, and we start like that, then we know that the integral of little f of x dx is going to be some family of antiderivatives, right? Okay, so that means you've got that, right? Okay. Right, so all I did here, right, is just take this piece here and substitute it in right there. Okay, just make sure that's clear. Right, there's kind of a lot of symbols flying around here, and this is, admittedly, we're being a little like loose and crazy with the derivations, but we'll get into more rigor in a moment. We're just trying to kind of set the stage here a little bit. So if we start with the integral of little f of x dx and we differentiate that with respect to x, then that's the same thing as differentiating the family of antiderivatives, okay, which is what? Well, we'll be very, very thorough here. That's ddx of big F of x plus ddx of the constant. What's the derivative of big F of x? That's just f prime of x. Okay, what's the derivative of the constant? That's just 0. And what do we know? Well, big F is an antiderivative of little f. And so that means when I differentiate big F, I need to get back to little f. Right? And so this piece here, right, when I differentiate the integral, I get back to the original function itself. And so this is another way to see how differentiation undoes integration. Differentiation undoes integration. Okay. And the same thing can be said of, well, sort of the reverse could be said here. Integration undoes differentiation. Okay. So there's a whole section on this phenomenon, this relationship between integration and differentiation. We'll get into that. It's a couple sections away. Maybe it's the next section, actually, but it's not too far away. I think it's a couple sections up. We'll get into this in tons of detail, but right now really what we're trying to motivate here is just this idea that when I do this operation called indefinite integration, what I'm doing is finding a class of functions that satisfy, that all sort of wrap up into the general solution of a differential equation, right? And the act of doing that is in nature sort of the reverse of differentiation. It's kind of it undoes differentiation. And conversely, right, if I have a class of antiderivatives, when I differentiate them, I get that those two are also reciprocal. I get back to the original function as well, right? So the two are related to each other. Okay, and this relationship is really amazing. It's remarkable, and really, when we get into the fundamental theorem of calculus, which is the section which explores this in lots of detail, we'll see even more on this. But to sum it up, integration undoes differentiation. Okay, and differentiation undoes integration. Okay, so the two are related. They're inverses of one another. All right. So I'm gonna stop the video there, and we'll pick it up just because this is a longer section. We'll pick it up in a part B. Okay, so we'll end part A with that.